The boiler room fell silent just after midnight. It was October 1891, and the evening shift at the Riverside Cotton Mill had brought the main steam line down for scheduled maintenance. The fires were drawn hours earlier. The header valves stood open to atmosphere. Somewhere in the cooling darkness, metal contracted with faint ticking sounds, the language of heat leaving iron. George Pemberton, the night engineer, walked the line with a hand lamp, checking each gauge as protocol required. Boiler pressure, 0. Header pressure, 0. Branch line pressure, 0. Everything read as it should until he reached the gauge mounted on the east wall, feeding the third-floor carding machines. The needle rested at 4 pounds. He stopped, set the lamp on a bracket. The system had been down for 3 hours. Every other gauge on the same header showed 0. This one did not. Pemberton tapped the glass face with his knuckle, a practiced gesture the kind engineers perform without thinking. The needle trembled, dropped slightly, then returned. Not to 0. To 4 pounds, perhaps a quarter pound less. It settled there as if it belonged. He opened the drain cock beneath the gauge. A thin stream of water ran out, then air, then nothing. He closed it. The needle had not moved. The pipe was cold to the touch. The valve upstream stood open. There was no steam, no pressure, no reason for the gauge to read anything but 0. Yet it did not. Pemberton stood in the near darkness, watching the needle. It was steadier than his pulse. He checked his pocket watch, 12:43. He would wait 15 minutes, he decided, to see if the reading changed with time. The lamp oil burned with a faint hiss. Condensation had formed on the brick wall behind the pipe, a sheen of moisture that caught the light. The building was cold now, the autumn air seeping through gaps in the foundation. 15 minutes passed. The needle had not moved. By morning, the gauge still read 4 pounds. Pemberton filed a report with the chief engineer, Martin Caulfield, who came down to see it himself. Caulfield was a practical man, trained in Glasgow, skeptical of anomalies that could not be reproduced. He brought a second gauge from the instrument room, a recent Ashcroft model, calibrated the month before, and installed it on the same tapping point. Both gauges now read 4 pounds. Caulfield disconnected the original gauge entirely, removed it from the pipe, and laid it on the workbench. In open air, away from the system, the needle dropped to 0 within seconds. He reconnected it. Within a minute, it climbed back to 4 pounds and held. "Test the Bourdon tube," Caulfield said. The mechanic removed the back of the gauge. The Bourdon tube, a curved, flattened brass pipe that straightens under pressure and drives the needle through a linkage, moved freely when manipulated by hand. There was no binding, no corrosion, no visible deformation. The spring mechanism returned the needle to 0 when the tube was relaxed. But when the gauge was reinstalled on the steam line, cold, open to atmosphere, drained of condensate, it read 4 pounds. Caulfield tried a third gauge, same result. He moved one of the gauges to a different location on the same header, 20 feet west. It read 0. He returned it to the original tapping point, 4 pounds. The problem was not the instrument, the problem was the place. Caulfield made notes in his engineering log, sketching the pipe layout and marking the gauge location with careful dimensions. He recorded the ambient temperature, 52 degrees, and the time elapsed since shutdown. He noted that the brick wall behind the pipe was damp, that the floor beneath showed rust stains from previous condensate drainage. Small details, perhaps meaningless, but he had learned long ago that mysteries revealed themselves in what others overlooked. The gauge face was clean, the brass case free of dents. The manufacturer's plate read Ashcroft, Boston, 1889. A good instrument, a reliable instrument, and yet... Word spread quietly among the engineering staff. It was the kind of problem that should not exist, small enough to ignore, precise enough to disturb. Caulfield ordered a deliberate test. He installed 4 gauges in sequence on the same mount, each from a different manufacturer, Ashcroft, Crosby, Schaffer and Budenberg, and a French Bourdon model from the Philadelphia exhibition. Each was bench-tested beforehand. Each returned to 0 in open air. Each read 4 pounds when mounted on the east wall tapping. The pattern held across instruments, across time, across conditions. Morning or evening, the needle stopped short. When the system ran under full pressure, 85 pounds, the gauges tracked correctly. When pressure dropped to 20, they tracked correctly. But during shutdown, with the header open and the pipe cold, they refused to read 0. Engineers from the mill's home office arrived in November. They brought calibration standards, mercury manometers, and a dead weight tester. The gauges were accurate. The steam line was vented. The condensate was drained. There was no measurable pressure differential between the tapping point and atmosphere. And still, the gauge read 4 pounds. One engineer suggested the pipe might be trapping pressure in a dead leg, a closed section where steam could not escape. They opened every drain valve on the branch line. They disconnected the pipe downstream and confirmed airflow. They left the system open for 2 days. The gauge read 4 pounds. Another suggested magnetic interference from nearby equipment. They moved the gauge 6 inches, then a foot. Then they isolated it entirely on a length of removable pipe. 4 pounds. By December, the anomaly had been documented in 14 separate tests. The gauge was not malfunctioning, it was reporting something, but what it reported should not have been there. The mill's general manager began asking questions. Maintenance schedules had been disrupted. The third-floor carding machines remained offline longer than planned. Caulfield assured him the system was safe. The anomaly appeared only during shutdown, never during operation, but he could not explain it. That bothered him more than he admitted. In 30 years of engineering, he had seen gauges fail in every conceivable way. Broken, corroded, miscalibrated, installed backward. He had never seen one fail by being too consistent. A pressure gauge is a mechanical translator. Inside the brass case, a Bourdon tube, shaped like a curved segment of pipe, flattened in cross-section, responds to pressure by straightening slightly. The closed end of the tube connects through a linkage to a gear and pinion, which rotates the needle across the dial face. When pressure increases, the tube straightens. When pressure drops, the tube's natural elasticity pulls it back into its curved rest position, and the needle returns to 0. This mechanism is simple, reliable, and depends on a single assumption, that the tube's rest position corresponds to atmospheric pressure. In normal operation, a steam gauge reads 0 when the pressure inside the tube equals the pressure outside, both at atmosphere, roughly 14.7 pounds per square inch. The needle does not measure absolute pressure, it measures difference. 0 on the dial means equilibrium. When a steam system shuts down, pressure bleeds off through valves, vents, and drains. Steam condenses into water. The temperature drops. The pipe cools. Within minutes, the pressure inside approaches atmospheric. The gauge should read 0 because there is no difference to measure. That is what should happen. At the Riverside Mill, the gauge read 4 pounds after the system had been open to atmosphere for hours. If the reading were accurate, it would mean the pressure at the gauge tapping point was 18.7 pounds absolute, 4 pounds above atmosphere, while the pipe was vented and cold. That would require a source, a column of fluid, a sealed volume, something maintaining a pressure differential where none should exist. The engineers began looking not at the gauge, but at the pipe. Caulfield spread the system drawings across his desk. Blueprint paper yellowed at the edges, marked with corrections in pencil and ink. The east wall line had been installed in 1884, part of the mill's expansion into textile finishing. The pipe was 4-inch wrought iron, black with scale and age. The drawings showed every valve, every fitting, every change in elevation. He traced the route with his finger, looking for places where geometry might matter. The engineer who had designed the system was dead. The contractor who had installed it had moved to Pennsylvania. The pipe itself was the only witness, and it was not talking. In January, Caulfield had the east wall section of the steam line disassembled. The pipe ran vertically from the basement header, rose 12 feet through a brick chase, then turned horizontal through the third floor. The gauge, tapping, a half-inch brass fitting threaded into the main pipe, was located just above the elbow, about 8 feet above the basement floor. When the pipe was opened, water ran out. Not much, perhaps a pint, but enough to matter. The condensate had pooled in the low point of the elbow, below the gauge tapping, in a section of pipe that sloped slightly downward before rising again toward the carding machines. Caulfield measured the geometry carefully. The gauge line, the short section of pipe connecting the gauge to the steam main, was 18 inches long and angled upward at roughly 10 degrees. The tapping itself was positioned such that condensate in the main pipe could not drain past it without being displaced by air entering through the open header valve. They dried the pipe completely, reassembled it, and let the system cool. The gauge read 0. They introduced a measured amount of water into the elbow, simulating condensate, and closed the drain valve below the gauge line. The gauge climbed to 3.5 pounds. They let the pipe cool overnight. The gauge read 4 pounds. Temperature mattered. When the pipe was warm, the gauge read lower. When it cooled to room temperature, the reading increased. The difference was small, perhaps half a pound over 20 degrees Fahrenheit, but consistent. Caulfield sketched the system in his notebook. A column of water, a sloped gauge line, a temperature-sensitive metal tube. The pieces were present. The mechanism was not yet clear. He conducted the temperature test 3 more times, varying the starting conditions. Each time, as the pipe cooled from 90 degrees to 50 degrees, the gauge reading increased by roughly the same amount. He checked the gauge line for obstructions and found none. He examined the threads of the tapping fitting under magnification, looking for defects that might create a one-way valve effect. The threads were clean and properly formed. He measured the internal diameter of the gauge line at multiple points. It was uniform. Whatever was happening occurred not because of a flaw, but because of the design itself, or rather, because the design had not anticipated this particular combination of conditions. In February, Caulfield and a consultant from the Ashcroft Manufacturing Company conducted a controlled reconstruction. They filled the gauge line with water to a measured depth, sealed it, and allowed the system to cool. As the temperature dropped, the water contracted slightly, but the brass Bourdon tube inside the gauge contracted more. Brass has a higher coefficient of thermal expansion than water. As the metal cooled, it pulled inward, reducing the internal volume of the tube and creating a slight suction effect on the water column. This contraction was not enough to create 4 pounds of pressure, but it was enough to prevent the gauge from fully relaxing to 0. The second factor was the water column itself. 18 inches of water, angled at 10 degrees, created a hydrostatic pressure at the base of the gauge connection. Not much, less than a pound, but measurable. Combined with capillary effects in the narrow gauge line, the water did not drain freely even when the system was vented. The third factor was elastic hysteresis in the Bourdon tube. After years of service under high pressure, the tube's metal retained a slight residual stress. It no longer returned perfectly to its original shape when pressure was released. The effect was minuscule, invisible under normal operation. But at 0 pressure, with no opposing force, the tube rested in a position slightly displaced from true mechanical 0. None of these factors alone would produce a 4-pound reading. But together, with the geometry of the pipe, the temperature of the room, and the presence of condensate, they combined. The gauge was not measuring steam pressure. It was measuring the interaction of thermal contraction, residual stress, and a trapped water column. The Ashcroft consultant, a man named Hewitt who had designed pressure instruments for 20 years, admitted he had never seen the effect documented. "We test our gauges in air and under controlled pressure," he said. "We don't test them with water columns at odd angles in cooling pipes." Why would we? Caulfield understood. The gauge was performing exactly as designed. The pipe system was performing exactly as designed. The problem existed in the space between them, in the unanticipated interaction of two properly functioning systems. That was the difficulty with industrial machinery. The failures that mattered most were not the dramatic ones, but the subtle ones that hid inside normal operation. The explanation, when published in the Transactions of the American Society of Mechanical Engineers in late 1892, was precise. A pressure gauge mounted above a condensate trap in a vertically oriented steam line may exhibit a false residual reading during shutdown due to combined effects of hydrostatic pressure from condensate, retained by pipe geometry, capillary action in the gauge connection line, thermal contraction of the Bourdon tube relative to the trapped fluid, and elastic hysteresis in the gauge mechanism following prolonged exposure to operating pressure. The gauge was accurate. It was measuring real forces, but those forces were not the ones the engineers expected. At the Riverside Mill, the solution was simple. They relocated the gauge tapping to a point above the elbow where condensate could not accumulate and installed a small drain valve on the gauge line itself. The new installation read 0 during shutdown. Caulfield kept the original gauge. He mounted it in his office, disconnected, the needle resting at 0. It had not lied. It had reported what was there, not steam pressure, but the ghost of heat, the weight of water, and the memory held in metal. Industrial instruments did not fail because they were imprecise. They failed because precision revealed complexity no one had thought to design for. In the age of steam, engineers learned to ask not whether a gauge was broken, but whether they understood what it was built to see. The paper drew modest attention. A few mills reported similar phenomena. Gauge manufacturers began including drainage recommendations in their installation manuals. Caulfield received 3 letters from engineers who had dismissed identical anomalies as instrument error. He answered each one. The work of engineering, he had come to understand, was not only building systems that functioned, but recognizing when function revealed something deeper, when the tools meant to simplify the world instead showed how much remained unmeasured, unnamed, and waiting in the space between expectation and reality. The gauge stayed on his wall for 30 years.